Can you just confirm that it's there for you, Humphrey?
Yes, it's
Right,
there.
excellent. Okay.
So
where we've got the theme of urgent material needs for Africa, I specifically thought then to address my talk regarding problems in the energy sector, and also aimed at the planning that South Africa has for a green hydrogen economy. Yeah. Sorry, I just need to do something here. Right. So we all know about the energy crisis in South Africa and Africa. Some days we might feel that the politicians say, crisis, what crisis? It's commonplace that we've got a number of old energy sources that are currently dominating the scene, and we've got the associated problems with those energy sources, and there's a global change needed in terms of our resource mix due to aspects like geopolitical instability. The war in Ukraine has changed the energy scene in Europe considerably. We all know about the problem of global warming, and Professor Knudsen also alluded to aging infrastructure being a problem in the energy sector. So this is a snapshot of the energy mix in America. We'll look at South Africa and Africa in a while, but it is largely dominated by fossil fuels, and renewables are only constituting 12% in 2020. What the world needs to do, obviously, in terms of the global challenges, is to actively decarbonize. And this slide just demonstrates that we're far away from that. And coal is the dominant source of energy. And if you compare natural gas to coal in terms of the CO2 production per kilogram, it is in the order of 7 times lower than that of coal, but natural gas is a pretty small percentage of the typical energy mix. There was a report that came out in 2021 talking about the production gap between global targets in terms of the greenhouse effect and where we are, in fact, in 2021. There was very little change from 2019. And it simply shows that if you actually analyze the plans of the various countries in terms of the CO2 production, in terms of consumption of the various energy sources, if you compare that to a 1.5 or 2 degrees Celsius target, reduction target, then there's a huge production gap. And in South Africa, the situation is shown in this particular slide. So we depended on 70% of coal at this stage. Natural gas is still pretty small, and renewables are very small. It's now in comparison to the United States. And I suspect that the situation is much the same in other African countries as well. So natural gas has a number of advantages due to higher efficiencies. Also show that slide in terms of the CO2 production, which is considerably lower. And natural gas has a number of good applications in industry, making it, as I said, quite popular overseas. And in South Africa, we're slowly picking up the consumption using natural gas. The transport of natural gas from point A to point B then necessitates a particular infrastructure. Much of that infrastructure is high-strength steel pipelines, and in my talk I will zoom in on that particular aspect. So this is a summary of the pipeline networks running from Mozambique into central South Africa, and also from the East Coast. These pipelines are mostly in private hands. And Transnet is also a big owner of pipelines. Again, this slide shows that most of those pipelines are concentrated on the eastern side of the country, running from the eastern coast towards central South Africa. And many of these pipelines currently distribute natural gas, specifically the big pipeline from Mozambique into Central Africa, Eastern Mpumalanga and the like, is 100% natural gas. So these pipelines are quite cost efficient and popular in a country like South Africa. They should also be quite popular in the rest of Africa due to our distances and the like. And the typical requirements for these pipelines, are that you need fairly high internal pressures, large diameters, and corrosion resistance. And due to these requirements, high strength steels or medium strength steels are then typically used for the construction of these pipelines. So again, to touch on the comments from Prof. Knudsen, steel is still quite often the trusted material to use in particular situations. So there are a number of international standards, both in terms of the material to be used for these type of pipelines, and also then for the construction of the pipelines, as well as the design. So I'm now moving over to the hydrogen aspect of my talk. Our government has very ambitious plans concerning the green hydrogen economy and what the future will hold for us in terms of green hydrogen. One of the main reasons for this strategy is the decarbonization priorities in South Africa as well. The benefit of the green hydrogen economy is obviously that you produce zero CO2. If you compare that to the previous graphs, it's obviously nirvana to a large extent. Various white papers have seen the light, such as this hydrogen adjust energy transition. And it's also true to say that many of the large industries in South Africa are also planning their own projects regarding green hydrogen. The fact then is that in the next number of decades, hydrogen will probably be utilized as a replacement for natural gas. The planning is that one will have large solar and wind farms, specifically on the northwest coast of South Africa and also in the same region in Namibia, that will produce green hydrogen through electrolysis. That hydrogen then needs to be transported, obviously, to the end destinations, being places that will consume the hydrogen. And that will typically then be in the central parts of South Africa, where large users will be for the hydrogen. But from the hub, say in central South Africa, the existing pipelines that are currently used for LNG distribution can be used for the distribution of hydrogen to the end users. And that is specifically then a topic that I'd like to touch on, because there is implications regarding the metallurgy of the existing pipes to carry the hydrogen to its end destination. So some of these challenges for repurposing existing pipeline networks are summarized on this page. So in the situation where a pipeline is, say, 20 years old or whatever, similar to the point that Rob made, the pipeline will probably have some accumulated damage due to materials damage mechanisms, also possibly mechanical damage. You have the fact that you say 500 kilometers of pipeline has a great number of welded joints, many of which perhaps have non-optimal quality. Cathodic protection is commonly used for these pipelines, and the failure or poor operation of these cathodic protection systems can result in hydrogen being generated on the external surfaces. The internal hydrogen can deteriorate the material through a specifically degradation mechanism referred to as gaseous hydrogen embrittlement, or GHE. Because the consequence of the failure of a pipeline carrying hydrogen at high pressure is very high, the pipeline integrity management systems of these pipelines will then need stringent adaptation. So currently, one has a situation where there's a very specific inspection strategy for a particular pipeline, and that inspection strategy has been developed to ensure that the possibility of failure, the probability of failure, and the consequence of failure is mitigated. When you now change to hydrogen, the consequence of failure is increased, and the probability of failure is also increased, and therefore the integrity management system will need adaptation. I think I'm going to skip a slide or two, just in the interest of time. Yeah, so obviously one has to now balance the benefits of repurposing an existing pipeline with the increased risks, and it will also mean, that there will be a specific metallurgical work that is required before one can repurpose the pipelines. So this slide just gives an overview of a number of pipeline failures. And I'm not going to go into too much detail here. So in terms of hydrogen embrittlement of pipeline materials, is a number of factors influencing that. So the material selection, specific alloy that is used or has been selected for the pipeline, the structural design is quite important. And there are a number of metallurgical strategies that can be considered in optimizing the resistance to hydrogen embrittlement. The particular selection of the chemical composition, the formation of carbides and precipitates for traps, how the hydrogen is absorbed, diffused and trapped, and in particular surface treatments can also be considered to enhance local hydrogen embrittlement resistance. So the mechanical properties in particular of these steels in the pressurized hydrogen environment needs to be evaluated, and this calls for fairly sophisticated testing equipment. The test method will have to ensure that you have the pressurized hydrogen environment and that you've got the sample inside and that no hydrogen escapes while you are straining the material, and this calls for quite difficult experimental setups. Point is that currently in South Africa we do not have the facilities required to do this type of test. The failure mechanisms and surface treatments then also need to be evaluated in the laboratory. So I've touched on some of the test methods that is required. Fatigue is also an issue in the sense of hydrogen service. I'll come to a slide showing that just now. And if you imagine now cycling a fatigue sample on a pressurized hydrogen, again, you require very sophisticated testing equipment. Microstructural assessments would be a central part of checking for integrity, comparison of microstructures A and B there, A being a vintage X52 and B being a hydrogen resistant low carbon pipeline material, clearly shows the effect of the development in the latter number of years in terms of a better microstructure. So this particular schematic at the bottom of the page shows the preferential diffusion of hydrogen towards a weld metal. This is now in the case of weld metal with tensile residual stress, and it then just demonstrates that the welds are likely to be the areas that will accumulate hydrogen damage more rapidly than any other region. So in the literature, there are a number of ways to check the impact of the hydrogen on the mechanical properties. Some of them are then also numerical methods. Experimental methods are obviously still the gold standard. So this slide demonstrates what happens to a fatigue environment with pressurized hydrogen. This is a fatigue rate growth curve, and it's been shown by many researchers that the hydrogen results in accelerated fatigue rate growth. So concluding remarks, I think I'm largely within my 20 minutes. Yeah, the concluding remarks is that what we found in our investigations is that high ductility carbon steels with slightly elevated strength X42, X52 grades are commonly used for hydrogen transportation pipelines. So typically one has a maximum pressure of 21 megapascal is allowed by a particular design code. The existing pipelines run up to 10 megapascal internal pressure maximum. So the girth welds are prone to hydrogen damage due to a number of factors such as the high residual stress levels. So the hydrogen embrittlement will be affected by both the concentration of hydrogen and also the particular loading conditions in the pipeline. And the actual load variations that you will get in the pipeline due to geological movement and the like can cause fatigue for these varied pipelines. And as I said, it's known that hydrogen accelerates the fatigue crack growth at high enough hydrogen pressures. And the bottom line then is that if one would consider repurposing an existing pipeline for carrying hydrogen, pressurized hydrogen, it will require quite a bit of metallurgical interventions and testing, and it will also require the redesign of the pipeline integrity management system. Thank you, Chair.
Thank you very much.